Devanand Mallayya M. is currently pursuing his degree Integrated BS-MS program of Indian Institute of Science, Education and Research at Trivandrum. He is now in his 6th semester with mathematics major along with physics and data science as minors. Today he will be speaking on mathematical application of Mādhava series approximation and convergence acceleration techniques. Devanand, you may proceed.
Thanks to Professor Michel and all the organizers. And I'd like to start my talk on the mathematical applications of Mādhava's approximation convergence acceleration. So the Leelavati from by Bhaskacharya is a delightful work from the 12th century area. And it was enormously popular, and its popularity led to a large number of commentaries and expositions. The most elaborate of which is probably the 16th century commentary, Kriya from Shankar and Narayana. This commentary has had a lot of additions and additions to it, and to expand the knowledge and to update it. And in this commentary, a lot of achievements of the Kerala School of Mathematics from the rightly called golden age of the history of mathematics of India is found. After the emergence of Mādhava, the Kerala School of Mathematics went through a huge upsurge in mathematical activity, and this period again is known as the golden period of the history of mathematics in India. Like Aryabhatta, the mathematicians of this in India of this period were aware of the problem of the incommensurability of the circumference and diameter of the circle. And Mādhava had to combat this problem had ingeniously devised an infinite series to evaluate the circumference of the circle. This contribution has been highlighted in many commentaries, the Thiruvananthapuram being one of them. And Shankara's exposition in verse 199 of the Leelavati goes into much detail about the same series. This series, in that, he goes Mādhava and puts the series as and then this series, as it is, converges extremely slowly, and you need a large number of terms to get even a moderate level of accuracy. So to combat this, he came up with a technique of adding a remainder term, which will compensate for the loss of accuracy from the truncation of the series. He does this by using correction factors and an error function, which he minimizes to find a correction factor. So the series comes to be of the form sum from Tn plus a remainder term minus 1 raised to n minus 1 Tn. And here this Tn would be the correction factor. So, for an ideal correction factor, the ideal correction factor for a large value of n, the nth term and the n plus 1th term of the series, along with the correction factor, would give the same value. So this would basically tell us what the error is by looking at the difference between the two successive terms, and hence we define the error function as the difference between the n plus 1th and the nth term of the series with the correction function as well. So he took so for an exact correction function, the difference would be 0, the error function would be 0, and using that we can derive a condition which would be Gn plus 1 plus Gn equals the n plus 1th term of the series. And in case of the pi series, which appears at the basis, comes out to be about 1 by n plus 1. And this could be possible if we can assume that Gn and Gn plus 1 they're both equal and are half of the n plus 1 term. But then again, Gn and Gn plus 1 cannot be the same. So, and hence a new correction factor needs to be defined, in which you add or subtract a constant on the denominator. Mādhava came with a value of 2. He subtracted 2 from the denominator and the correction function became 1 by 4. The logic by which this number 2 was reduced was not mentioned in any of the commentaries, but it can be reduced that you can find 2 by assuming it to be an arbitrary constant. So the denominator is a polynomial, and then you minimize the error function with respect to this constant. When you do that, you find out that the minimum here happens when a is 2, or the arbitrary constant is 2, is minus 2. So then the new question is this. And the error, which in the first case would have been the difference between the n plus 1 and the nth term, if you are not using a correction function, would be would have a first degree polynomial in the denominator. And this, with the first correction function, it has a third degree polynomial. So this already converges much faster than the normal series. But then, even though it's much better than the unmodified series, it still takes an extremely large number of terms to get accurate values. And Mādhava was not happy with this error, so he came up with the second order correction function, which you get by adding a fraction of the denominator to the denominator itself. And there will be an arbitrary constant in that as well, and we minimize the error function with that as well, and that comes out to be 4. So then the second order correction function comes out to be n by 4 and square plus 1. And with this, the error function has a denominator which has a polynomial of n to the 5th degree. So this is even more rapidly convergent than the previous one. We can continue to derive higher and higher order correction factors for the series by just continuing to add the fraction of the denominator itself, and then minimizing for the constant. And drawing inspiration from this continuous technique, I have tried to apply this technique to other alternating series and derive the corresponding correction factors and error functions, and study the FIC, that is how much faster the modified series is converse compared to the original ones. And I'll discuss 2 of those cases here, and in all of those cases, the results obtained were excellent. First, I'll discuss the alternating harmonic series. And for this, the correction function by applying the technique comes out to be this continued fraction, the convergence of this continued fraction. Similarly, for the Kaplan series, which would be 1 by 1 minus 1 the whole square, the correction function comes out to be the successive convergence of this fraction, of this continued fraction. The series is pretty significant. It's the Kaplan series. It converges to the Kaplan's constant, which is named after Eugene Kaplan, who discovered infinite series expression for the computation of the constant. Kaplan's constant is it's a quarter of the volume of an ideal hyperbolic octahedron, and it appears in many fields like combinatoric statistical mechanics, number theory, and even in physics to calculate the mass distributions of parallel galaxies. Now I'll discuss the results that I got by evaluating the series and finding out how many terms it would take to get to a desired level of accuracy. So for the original Mādhava series, for the pi series, we need about 10 raised to 7, the order of 10 raised to 7, an impractically large number of terms to find pi to the 9th decimal place using the raw series. But then when you use the first correction function, it reduces down to 652, and then goes to 49 with the second, 18 with the third, and 11 with the fourth. And using higher order correction terms will result in even faster convergences. And similarly for the coordinate harmonic series, the result comes out to be similar, about 10 raised to 6 terms without the correction function, and 83 with the first, 30 with the second, 3 with the 13 with the third, and 8 with the fourth order correction. for the Catalan's constant, it converges much faster than the Mādhava series and the Log series, but it still takes about 3,600 terms to 1,700 terms to calculate the constant of 8 decimal places. But then with the successive convergence, it takes about 25, 8, 6, and 4 terms. And, these results are excellent, and they definitely have practical application. I'd like to explore this further, and I plan on making up series which would have even faster convergences by using the error functions. And, they would yield even better results. So, if anyone has any questions.
So thank you, Devanand, for the talk. Even though there were some initial glitches, you could manage very well to present. Now we are open for question and answer session.
Can I ask one question?
Yes.
You see, Devanand, can you hear me?
Yes. They can.
Yeah. You see this this pi by 4 series, okay? The Mādhava series, okay? Hello.
Hello. Yeah, you're audible.
You see 1 minus 1 by 3 plus etc.
Yeah.
Then the remainder term, right?
Yes.
So now for log 2, what is the remainder term? Can you show me? Log 2. Log 2. What is the remainder term you have written?
Yeah. This one. I have not specifically shown the remainder terms, but they all come out to be like this continuous fraction. We can get all the remainder terms from this. So for the first remainder term, it come out to be 1 by 2 n plus 1. So second will be 1 by 2 n plus 1 plus 1 square by this continuous fraction.
Oh, you found this? You found this continuous fraction?
Yeah, and I just applied the same technique that was used in the pi series.
One more thing, you see, in one of those things, there are also negative terms. Can you show me? There's some negative. Yes.
No, as in this is like negative terms become smaller and smaller, so it doesn't really go to negative.
No. So are you using some nearest integer continuous fraction, something like that? Nothing like that?
No, nothing like that. This is a normal pattern. I just put the negative so that it's easier to write it.
Okay. Because Venkatesh for pi and myself, we have worked on this Drukarana. There this nearest integer continuous fraction is there. So I see. You put it. That is not nearest integer. Yeah. Okay. May not be. Okay. Very good. I think it is interesting. Yeah, but you should try to write the form of the remainder term. Yeah, maybe.
Okay. Yeah, I can specify the remainder terms for the. Okay.
Yeah. See, like Mādhava has given 2-3 forms of the remainder term, right? Yeah. So now, if you can also give some form of the remainder term, it will be very interesting.
This contains all the forms. As in the first form would be you just put 1 for n and then ignore all of the others and just 1 by 8 n square plus 6.
Okay.
So we just add the successive term in the continuous fraction and we get the next order the correction fraction.
Okay. That's quite good. Interesting. Yeah.
Thank you.
Yeah.
Devanand, there is a question by Jai. Hello.
Yeah. To the references.
Yeah, he's asking whether you can confirm that these corrections were used by Mādhava.
No.
As in the corrections are used by Mādhava for the pi series.
Pi series, yeah.
So the pi series was used by Mādhava, and I just took the technique and applied it to other series. I don't think it has been done before.
I see.
And Pranati is asking whether you could show the references again. references. Yes, yes. Okay.
I just have one question about this series error term, which has negative numerators that was mentioned by Professor Sriram.
Yeah.
This series that we have is an alternating series, and therefore the correction terms, they are also expected to be alternating.
Yeah.
So, is it that this continued fraction that you have mentioned, this gives you such alternating values because there are some negative things also in the numerator?
No, no.
So,
The value that comes out of the fraction, you have to multiply minus 1 is 10 minus 1 to that. So that the
you have
minus
to
1
multiply
is
by
10
that.
minus 1 term makes it automatic.
Thank you. Yes, right. Okay.
As in this fraction gives Gn and the series is yeah, the fraction gives Gn and the series
Okay.
has
You have to multiply.
it has a sign applied to the Gn.
Thank you.
So are there any other queries?
Can I make a comment?
Yeah.
Please.
So first of all, this is an interesting subject, and it's an important subject that should be explored. And I think also that it's a good idea to try to get new results, if possible, on the basis of these methods, as long as they are clearly separated from those that are actually in Mādhava's text. It would be nice to compare these methods with modern methods for acceleration or convergence, of which there are quite a few, starting with Oliver and people like that. But my question was about one small point in your talk. You define capital En, and you call it the error function. It's still on the slide that we see here. But this is not the error. This is the correction that needs to be applied at step N. And this is a moot point because one of the conceptual advances in the Mādhava school is that they seem to have conceived an actual limit of a sequence as something that's actually attained. So there is the issue of an actual infinite that's occurring here. It's very clear in the argument where you have in the Yukti Bhashya the limit of the sum of powers 1 to the k plus etc. n to the k, and there's an equivalent for that which is actually used. Now, if you call the error what you call the error, then the actual sum of the series doesn't appear anywhere. So the main conceptual progress is hidden. I got the impression, although there are experts in the Yukti Bhashya here that may be able to confirm that or not, that what is called the Staudion, that is the degree of...
Is that called the Staudiya, the error feature?
Is the Staudion this En, or is the Staudion actually supposed to mean the difference between Sn and the actual number that we want to have, that is the sum of the series?
Under the text, it is the difference between the n and the n plus 1 term. As in, when the series limit is attained, then the Staudiya becomes 0. That is
not attained. I mean, that's precisely the point.
Yeah. So,
and that there is a passage in which Nilaganda, I think, says that that he explicitly says that it's not possible to get an exact value of pi because there will never be a stage where the remainder is 0.
Yeah, but then if you extend the pi series to infinity, then the remainder might become 0. The equation of the Staudiya to 0 is not entirely rigorous. It's not a hard and fast rule. We equated it just to get a starting point for the correction function. Then after that, we just minimize the error, minimize the Staudiya, so that we can get a better correction function.
But you see what I mean. If this is what Mādhava is saying, it means that he doesn't have clearly the concept of the sum of an infinite series. What you're saying that he believes that after some point n, Sn becomes exactly equal to, it doesn't change at all.
No. In this, the statement was the if there is an ideal correction function, then at some point the convergence will become exact. There is no ideal correction function; it will always have a small amount of solver. But then, just to get a starting point to find the error function, we are equating it to zero, and we are putting in the concept that it can be zero if there is an ideal solver. And using that, we take an ideal Gn being half of the n% term. But then we also acknowledge that it's not possible for Gn and Gn plus 1 to be the same. And then we change the function and get a different correction term. And then we minimize the Staulia for that. So that is how it's taken. So the Staulia never actually becomes zero unless we take it to actual infinity.
Right. I would suggest not to call it the error because it's misleading because of this issue.
Okay.